Hi, I'm Trek, and this is my second video in my series on calculus. Today we'll be covering limits and the basics of their concepts and just introductory usage. So let's just jump into it. Here on my screen here I have a function here that we're going to be working with. X minus 1 multiplied by x squared plus x plus 1 over x minus 1. So you might ask, hey Trek, how come we don't just divide out this x minus 1 and this x minus 1? And I would say, well, you can do that, you can, but it's very important that you make a certain distinguish a certain fact about this function before you do that. And that's that you have to assume that x is not equal to 1. Because if x is equal to 1, then our quotient here is undefined, and thus we have a hole. So in order to divide these out, you have to put off to the side that our domain does not include 1, which is what this hole is for. But what's interesting is that this line this curve of this function doesn't seem to care too much that it has a hole right there. I mean, it doesn't seem particularly consequential. It seems to just keep going as though it didn't have a hole there. And that's what I want to talk about. I'm going to put a few points. I'm going to plug in some numbers that are near 1, and I want to see what values we get out. I have here the point 0.9 and f of 0.9, which is going to plug in. It's going to put us a point right here, and it's going to give us the value of 0.9 of the function, which is right there. I'm going to zoom in so you can see that a little better. So 0.9 and 2.71. Simple enough. And on the other side, I'm going to put a point there as well. So we're going to do 1.1 and f of 1.1. That's right here. And then I'm going to do something interesting. I'm going to put a point that's even closer to it down. 0.99, which will be in here somewhere, and f of 0.99. Oh, that's even closer. Let me turn these off. And 1.01 and f of 1.01. You can't even see that because it's closer. I'm going to zoom in so we get more space between these 2 points. So that's 1.01 and f of 1.01, and 0.99 and f of 0.99. And I'm going to take this step again. I'm going to go even closer. I'm going to go to 0.999 and f of 0.999. And then 1.001 and f of 1.001. We're going to zoom in so we can see them. Alright, by now you should be able to see the pattern that the closer we get to 1, the closer our value of the function gets to 3. As you can see, it's approaching on both sides, and our other points we're also getting closer to 3. So we have 2.97, 2.997, and what was our other one? Where are you? Anyway, the other one I think was 2.7. Yeah, 2.71. And for every single value we choose, there exists a value closer to x equals 1. So we could choose, we can go out however many decimal places, but no matter how many decimal places we go out, we can always find a value that's closer to 1 than what we picked. We can get, we can continue to enumerate values that are closer to x equals 1 forever. And with every single one of those values, there's going to be a function value, like f of that value, that is even closer to 3 than the previous one. This is sort of the fundamental concept behind a limit, is we have values that are approaching a certain value, even if that value doesn't necessarily exist in the function, like it's undefined. Everything is pointing towards it. Alright, so I'm going to jump to our next example. Actually, well, yeah. Okay, so let's talk about this one, because this is a very similar case. Here we have the function f of x is equal to the absolute value of x. On the left-hand side, we have a line here, and on the right-hand side, we have a line here. Now, I want you to notice that as our x value approaches 0 from the right side, we're approaching 0, Just watch my cursor here. And we're getting closer and closer to the value 0. And the closer and closer we get to 0, then our f of 0 becomes 0. All right. At the closer and closer we get to our x value of 0, the closer and closer we get to a function value of 0. We can trace and notice that as we get closer and closer, our function value, which is on the right, is getting closer and closer to 0. And no matter what value we can pick a value that's closer to 0, and we'll get a function value that's also closer to 0. Likewise, on this side, we can do the same thing. We can get closer and closer to x equals 0, and as we do, our function value gets closer and closer to 0. And for any x value we can pick an x value that's closer to 0 than that, and get a function value that is also closer to 0. This is part of the definition of the limit, which I'm going to describe to you now, is the limit of a function is the value at which both sides of the function are approaching. So, I'll write this down. The limit, put it down here. The limit as x approaches some value c of some function f of x is what the function approaches from both sides as x nears c. So in this particular case, the limit as x approaches c of f of x, which is our absolute value function, is 0. At least if c is equal to 0. So if we write this, what's the limit of x approaches 0 of f of x? That is equal to 0. Alright, so I'm going to go through a few more examples just to sort of hammer in the concept. So we have our absolute value function here. Let me show you the ceiling function, which ceiling is where you round up. Everything is rounded up. So 0.5 has a value of 1. 1.5 has a value of 2. Everything from 0 to 1 has a value of 1. And everything from 1 to 2 has a value of 2. This is an example of something not having a limit. For example, let's evaluate the limit of f of x as x approaches 1. All right, well let's take a look. Let me move that. So right here we have our 1. On the left side, we've got 0.7, and as we get 0.4, 0.5, 0.6, and as we get closer and closer to 1, notice our function value is also approaching 1. And for every single x value that we pick approaching from the left, we can pick another x value that's even closer, and our function value will be just as close to 1, if not closer. In this case, it'll be just as close. But the point is, it is approaching the value of 1. However, if we approach 1 from the right side, notice that as we get closer and closer to 1, our function value is not approaching 1, it is approaching 2. It is approaching a different value than from the left side. This function does not have a limit as x approaches any of the integers, 0, 1, 2, 3, 4, 5. At those points, this limit is undefined. However, we picked a point somewhere in the middle, like say, what is the limit as 1.5 of f of x. That is defined because, as you can see, if we get closer, 1.5, sorry. As our x value gets closer and closer to 1.5, our function value is approaching 2. And likewise from the right side, as we get closer and closer to 1.5, our function value is approaching 2. Alright, let's move on to the next example. Alright, this right here is a polynomial. I'm going to tell you right up front that polynomials have a unique property when it comes to limits, and that's that they always have limits at every single point. It has something to do with continuity, which we won't be going over too heavily, so just trust me for a moment. Basically, since this has no undefined points, it has limits at all points. That's not necessarily true because you could have piecewise functions, which we're going to talk about in a moment. But if we pick any sort of limit, like let's just say the limit as x approaches 0.25, which is right here, then actually let's do 1. Let's approach 0.5. As x approaches 0.5, notice that our function value is approaching 3, and for every x value we could pick an x value that's closer to 0.5, and its function value will also be closer to 3 than the previous one. And we can do that from the right side as well, getting closer and closer to 3. This has a limit at the limit as x approaches 0.5 of our L of x function is 3. Alright, next one. This is another example where something doesn't have a limit. Oh, sorry. Get rid of that stuff. So, this is an interesting function. If you notice, as x approaches 0 of our sine of 1 over x, the frequency of the sine wave just goes crazy. I mean, it's just, and no matter how far we zoom in, it's even crazier. I mean, as this gets infinitesimally small, and as we just get bands that are just right next to each other until it's just solid. So as, look at this, it's mind-boggling. So as x approaches 0, we actually don't have a limit because it doesn't approach a particular value. It approaches an indeterminate value. It approaches multiple values, basically. We have no idea what value it eventually reaches at 0. Because at 0 it's undefined, and at everything close to 0 it's approaching, completely arbitrary numbers and different numbers at each step. If we pick one value for x, it's going to have an f of x value, but the very next value of x is going to be approaching a very different number. It'll approach 1, and then -1, then 1, then -1, and it'll just keep going back and forth over and over again. So this has no limit at x equals 0. Alright, let's move on to the next one. Okay, so this one's an important detail. I think it's over here. So x equals 2. Yeah, okay, there it is. So, we're going to talk about the limit of g of x as x approaches, h of x. The limit of h of x as x approaches two of h of x. Come on. So, from the left side, we are approaching 2, and as we approach 2, notice we are getting closer and closer to the value of 4. And for every value that we pick along here, we could pick an x value that is closer to 2, and we will get out a value that is closer to 4 than the previous one. We can do this infinite times. On the other side, though, approaching the value of 2 from the right side, we are approaching 1 instead. They have different values that they approach, and thus the limit at 2 does not exist. I am going to take this opportunity to talk about left and right limits, which are not true limits, but they occasionally get used in mathematics. You might see something like this. So the limit of as x approaches 2 minus of h of x. As you come up to cases where this sort of thing is done, what this basically means is what is the limit from the left side, not the right side. Yeah, we don't care about the right side in this case. So, but evaluating this, we would get a value of 4, because from the left side it is approaching a value of 4. If we instead were looking for the limit as x approaches 2 from the right side of h of x, we would get a value of 1, because from the right side we are approaching the value of 1. Basically, both the left and the right side limits have to be equal to the same thing for the function as a whole to have a limit at that point. Alright. Next example. You also might see things like this. We won't take too much time on this one. This is just a combination of our g of x and our h of x, where on one side you have it approaching a fairly obvious value of, what is it approaching? 4? But on the other side it's approaching many values. So just look at this. It has an indeterminate value that it approaches. In this case, this function has a left limit at, what is this x value? Oh, it's 2. So it has a left limit at x equals 2, but it doesn't have a right limit at x equals 2. So this limit of this function on the whole does not exist at x equals 2, because one side of it doesn't equal the other side, and because the limit on the right side does not exist. Alright, so hopefully this should give you sort of a conceptual sort of overview of limits. It is a very sort of intuitive evaluation. Like, there's not necessarily algebra you do about it. There is one trick, though, that you could sort of do while you're working with limits, and that's what we did in the first example, where we divided out x minus 1 over x minus 1. Since we know this function is continuous, or not continuous, but it has limits at this point, we can go ahead and ignore the x can't be equal to 1 problem and go ahead and divide this out and evaluate it here. Which, this is just a polynomial, and like I mentioned earlier, they have limits at every point. Alright, so let's move on to our last section, which is the squeeze theorem. So the squeeze theorem is something you see a lot as we go on throughout calculus. We won't be using it necessarily in the near future, but you see it a lot, and it has heavily to do with limits, so I figured it'd be best to cover it now. But the gist of it is that you can take the limits of two functions to find the limits of a third function. So here we have our f of x equals absolute value of x, like we did in the previous example, and we know that it has a limit as x approaches 0 of 0. Its limit is 0. Likewise, we have the negative absolute value of x, and it's just the inversion of this. It also approaches 0. See, as we approach x equals 0, our function value approaches 0. And from both sides. And we want to know what the limit of our h of x function is as x approaches 0. So how we use the squeeze theorem is we need to prove that h of x here is less than f of x at as x approaches 0. So let's go ahead and do that. So for the moment, I'm going to take away this x, just because it's easier to talk about cosine for the moment. Notice that cosine always has a value between 1 and negative 1. And that means that if we put the x back, that our total value cannot actually exceed x, because this section here is always going to be a value between 1 and 0, 1. So this is going to be either 1x or negative x or something in between. So it varies between x and negative x. Our f of x, this is the line of y equals x, and this is the y equals negative x line. So the f of x also varies between x and negative x. And same with this one. So these are sort of our boundaries. This is the y equals x line, and this is the y equals negative x line. And we just explained why our x cosine of 1 over x is always between x and negative x. Now, Since we know the limits of this one and the limits of this one at x equals 0, we can use the squeeze theorem to prove that the limit of this one has to be between the two, or equal to. And since this one has a limit of its limit is equal to 0 as x approaches 0, and this one's limit is also equal to 0 as x approaches 0, then we know that the limit of x cosine 1 over x has to be equal to 0 as well, because it's between those two. The squeeze theorem is incredibly useful, but it's always done differently. So it's important to just sort of get the conceptual understanding of this. I've sort of put it in English, I guess, as best as I thought it could be phrased right here, and that's if f of x is greater than h of x as x near c, and g of x is less than h of x as x near c, then and both f of x and g of x has a limit at c, then the limit of h of x must be between or equal to the limits of f of x and g of x. You take two functions, and you take their limits, and you squeeze the limit of a third function and prove that it's in between the two, or equal to. In this case, it's equal to, but you occasionally just prove that it's between the two. So that's it. After this, we're going to go back to our derivative example, and we're going to finish that out, and then we're going to work on some more examples on all sorts of things. So I'll see you then. Enjoy.